All right, hello again, Ling 341. Today we're going to talk about harmonics and get started on our analysis of the acoustic structure of speech sounds. And I guess I'll preface this with a couple of different comments. One is that normally this is the point where we start covering this basically after the midterm, and acoustic phonetics is a bit strange. You have to kind of expand your mind in new and uncomfortable ways to get a grip on it. And so if you go through this lecture and the next one on resonance and feel like you're not really understanding what it's about or how it works, don't worry too much. That's a normal response to this stuff. And so in some respects, it's kind of useful that I'm recording these lectures and you can go back through them another time if you want to, if you don't get it the first time. But basically, don't freak out. This stuff is complicated, and we're going to try to walk through it slowly and from a couple of different perspectives in the hopes that you'll be able to get it by the time that we're through. Yeah, and it's also going to involve a little bit of math, but we've kind of been through the worst of the math part at this point. And I guess I'll also say that this lecture is kind of a nostalgia trip for me as well, because this is the very last lecture I gave before we went into lockdown back in the spring when the pandemic hit. And it's actually 8 months to the day. That was March 11th when I gave this lecture, and today it's November 11th. So a lot has changed since then, but this lecture is still basically the same. One of the things that I haven't changed from this lecture since then is this little intro bit. So like I said, this is usually one of the first lectures after the midterm for this class. And in the midterm, people have to draw mid-sagittal diagrams of various sounds. And it's also, I used to teach this class in the fall. And normally this lecture would be delivered around Halloween time. Right now it's November 11th, so we just passed Halloween. And kind of for fun and kind of for Halloween's sake, I at some point in the past took some of the more spectacular mid-sagittal diagrams and collected them all into a couple of slides for your benefit. And I did this last spring because the pandemic or the disease, the coronavirus, was kind of scary at the time, and it was kind of a way to lighten the mood a little bit while also kind of acknowledging that things were getting freaky. So in the interest of a bit of freakiness, here are some fun mid-sagittal diagrams. Here's one that is kind of what I was looking for in the midterm. This I think is from a couple of midterms ago, but this is for the sound theta. So you see that there's the tongue in between the two rows of teeth there. So it's interdental, and there's no voicing back here. And it's basically a fricative because, there's just a narrow constriction in between the teeth and the tongue there that you blow air through. So that looks great. And generally speaking, this looks like a human being, maybe with a very strong jaw. But either way, some of these other mid-sagittal diagrams are, interesting. They make you wonder a little bit what some of these people think about human faces. But they're kind of fun to look at, and maybe we can laugh at ourselves a little bit because these things are not super easy to draw if you haven't had a lot of experience with them. So some of these are supposed to be theta, and some of them are supposed to be the retroflex nasal. Yeah, and some of them work better than others. I had a couple more on this slide as well. This person just said drawing is hard, although they did a pretty good job at drawing a voiced retroflex nasal here. So yeah, it may be hard, but you can get there even without the best art skills. And this person said, moral of the story, tongues are effing weird, which is true, but they're so useful. They're impossible to ignore because we use them all the time, right? For speech and eating, all sorts of fundamental life necessities. Okay, so where are we going? This repeats a little bit what I said at the top of this lecture. So we're going to start harmonics today. We're going to do resonance next time. And I guess I'll point out as well that since this is the last lecture that I gave in person in the spring, after that, I started recording lectures at home like this. So this will be the last lecture of this series that you'll see me in video form, and then we'll go back to the things I recorded in March. But those lectures are still good. They'll just kind of be in a different setting and a slightly different format. But basically, we're going to cover acoustic phonetics. And this is difficult but fun because it will give you a huge amount of power in terms of how you can analyze speech. You can start to be able to see sounds better than you are able to hear them because, as we know, our minds kind of tell us a story about what they're hearing based on the languages that we speak natively. And if you can kind of see what's going on acoustically, it's a little bit easier to interpret how to transcribe speech than it is when you just start listening to it. For that reason, because you're well, your computer or the principles we use in acoustic phonetics are not going to be based on strictly like a specific native language. They're just general physical principles. And like I say here, it's going to get worse before it gets better. So it's a little tricky, but just stick with it. We'll get there. There's also a supplementary reading on today's lecture that I posted to the course webpage, and I'll show you where that is in the readings tab, or I guess the handouts tab. Maybe I should have, yeah. So check this ahead of time. But at the bottom here, this is when I posted it back in March. But this is an additional reading, Elements of Acoustic Phonetics by Peter Latifogo, just a few pages that kind of walks you through what he calls wave analysis. So we're going to do something similar to that today, but this will give you a reading to kind of back up what I'm going to tell you in this lecture. So what are we going to cover in this lecture? So basically at this point, we've learned how to calculate the frequency of a periodic wave, or kind of the relationship between frequency and period. And then we've also talked about the amplitude, or different ways of measuring the intensity or loudness of a sound, like amplitude, peak amplitude, RMS amplitude, and intensity, right, in terms of decibels. And those apply to complex waves, which are really what we're going to focus on here today, because most of the sounds we encounter in life are complex. Okay, so today what we're going to do is we're going to start combining these two elements of acoustic phonetics together. We're going to combine frequency with intensity and see what we get at the end in terms of our analysis of complex waves. Okay, so just to review complex waves. When you get more than one sine wave added together, they form a complex wave. And they are going to generally be periodic, but they won't look like a sine wave does. The way the math works, as we walked through before, you can take the amplitude value of one sine wave at a particular time and add it to the amplitude value of a different sine wave at the same time, and you get the amplitude value of the complex wave. This is just this algebraic notation I'm using, and I've walked you through, I think, the subscripts and what they mean before, but basically you have to just kind of line up the two sine waves in time, and you get a value for a complex wave in time, which, like I said, may repeat over time, but it won't necessarily look like a sine wave. So in graphical form, we've had this example where we take one waveform with high amplitude and low frequency. So this one goes up to +1 at its peak, down to -1 at its lower peak, or its minimum, I guess you would say. And it repeats 4 times over this little window of time. We'll say maybe it's a second, so that would make it 4 hertz, right? It repeats 4 times in 1 second. This one repeats more often. I think we calculated this one repeats 12 times in a second, so it's 12 hertz. And then its amplitude is lower. So its peak amplitude is about like a half here. And at the bottom, it goes down to -0.5 as well. So those two sine waves differ in those two respects. Those are the two properties that we need to know for a sine wave. Its peak amplitude and its frequency. And that's kind of all we need to know for a sine wave, because otherwise their shapes are always going to look exactly identical to each other. They just change along these two different parameters. But when we add those together, we get something, like I said, that's not a sine wave and has some complexity to it. And we need to know a little bit more than just its peak amplitude and its frequency to understand what puts it together, how it got put together, I guess you could say. So this one is a nice convenient one because we see kind of the big loops that we get from this original sine wave, and then we also kind of see the little loops on top and the bottom of this pattern that kind of look like they come from this smaller or second sine wave. So you can kind of see how the two are superimposed on top of each other there. But normally speaking, when you add sine waves together to get a complex wave, you're not going to be able to kind of look at the complex wave and say, oh, I can see where the two elements came from or whatever. They can be really complicated, and it can be very hard to see what the underlying sine waves are in them, if at all. Okay, we also learned about how to calculate the fundamental frequency of a complex wave. So when you combine sine waves, that will result in a complex periodic wave, and the complex wave has a frequency which is the greatest common denominator of the frequencies of the component waves. So we had to do a little bit of math to work through this, but basically, as a reminder, the greatest common denominator is the biggest number by which you can divide both frequencies and still come up with a whole number. And I think I've got some examples here, or at least one, right? So let's say I took a sine wave of 300 hertz and added it to a sine wave of 500 hertz. It would give me a complex wave, and that complex wave would have a fundamental frequency of 100 hertz. Yeah, so again, these numbers, 300 and 500, can both be divided by this number, 100, and you will get a integer or whole number result from that division, right? So 300 divided by 100 is 3, 500 divided by 100 is 5. There's no number bigger than 100 that will get you that sort of result. So if you took like 200, 300 divided by 200 is 1.5, 500 divided by 200 is 2.5, so that doesn't work, right? Anything bigger than 100 won't be the greatest common denominator of these frequencies. We've walked through that before, so I'm not going to walk through it again any more than I already have, but hopefully that makes sense. And if it doesn't, feel free to go back through that slide again or the previous time I talked about that until it does. But the question I want to ask now, which also might help you understand what's going on here, is why? Why is the fundamental frequency of this complex wave the greatest common denominator of the frequencies of these waves? Okay, let's think about the flip side of that idea. And for this, I want to talk about a concept which you don't normally hear about because maybe I just made it up, but it still works. You can think about the smallest common multiple of the periods of the component waves. So on this previous slide, we're talking about the greatest common denominator of the frequencies. And remember, in acoustic phonetics, or just talking about sine waves in general, frequency equals 1 over the period of the wave. So I'm not going to talk about the frequencies. I'm going to talk about the periods. I'm not going to talk about the greatest common denominator. I'm going to talk about the smallest common multiple of the periods of the component waves. So what do I mean by that? So both component waves that I'm adding together to get the complex wave are periodic, and that means they repeat themselves in time. So the pattern formed by combining these component waves will only start repeating itself when both waves start repeating themselves at the same time. And actually, this is useful enough that I will write it out in a separate document. So normally I try to focus on this in class, but we don't have a chalkboard here, so I'm just going to focus on it in Microsoft Word. So I'll write that down there, and you can think about it for a while. Maybe you can write it out yourself. That might also help you remember it. But basically, we're going to get a pattern, a complex pattern, and that will only start repeating itself when both of the component sine waves start repeating themselves at the same time. I'll walk you through how that works. And I'm going to walk you through that with a 3 hertz sine wave and a 5 hertz sine wave. And actually, I think before I do that, I'm going to kind of verify, what I said before about the, greatest common denominator of these waves being the fundamental frequency of the complex wave. So this is really simple math. What I'm going to do is add together 2 sine waves of the same amplitude. I think I showed you this before, but when we use this formula creator in Prot, this is the peak amplitude of a sine wave, and this is its frequency in here, and you don't need to worry about this 2 times pi stuff, although you could read more of that Peter Ladefoged book if you really wanted to. And I'm going to just add 2 different sine waves together, one with a frequency of 5 hertz and another with a frequency of 3 hertz, and we'll say 3 hertz, 5 hertz. So add those together, and so before we had, we're talking about a couple of sine waves with frequency 300 and 500. We're just dividing everything by 100. So the fundamental frequency of this guy should be 1 hertz, right? And we can take a look at it, and it's got this complex pattern like this. I'm going to turn this off. Can't really hear it because we can't hear sounds that are this low in frequency, and also it's not super intense either. But actually, I'll show this to you in a different way. We're going to make it longer. So it's only 1 second long in that original incarnation. I'll make it 3 seconds long. How about that? And yeah, now you can see the pattern repeating itself. So it kind of goes down and then kind of goes up. Blah, 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 blah. Yeah, so this is one repetition of the pattern here. This is like the second repetition of the pattern here. and this is the third, right? So I'm getting 3 repetitions in 3 seconds, and if I go from kind of the beginning of one pattern to the next, I get a period of about 1 second. So 1 repetition in a second is a frequency of 1 hertz. Okay, so this is happening because of this principle. The pattern formed by combining the component waves will only start repeating itself when both waves start repeating themselves at the same time. So what's happening here? Starting from 0 seconds, a 3 hertz wave is going to repeat itself at 1/3 of a second, or 0.33 seconds, at 2/3 of a second, 0.66 seconds, or 1 second, so on and so forth. A 5 hertz wave, which has a period of 0.2 seconds, will first start repeating itself at 0.2 seconds. Then the next period will be at 0.4, the next at 0.6, the next at 0.8, and then eventually it gets to 1 second. And so in between 0 and 1 seconds, these 2 sine waves are kind of just doing their own thing, repeating whenever their period elapses or moves on to the next repetition. So this one will repeat at 1/3, at 2/3, so on and so forth. And then they kind of wind up aligning at 1 second. So there's another way I can walk you through this, and which is the way I normally do it in class as well. So this is repetitions at 1/3 of a second, 2/3 of a second, 3/3 of a second, right? Which is how we get 1 second, right? So it starts at 0, then at 1/3, 2/3, 3/3, so on and so forth. And then here we get repetitions at 1/5 of a second, 2/5 of a second, 3/5 of a second, 4/5 of a second, and then finally at 5/5 of a second, which is that 1 second. So they're repeating themselves. These individual sine waves are repeating themselves in time, but the pattern formed by combining these sine waves is only going to start repeating itself when both of those individual patterns start repeating themselves at the same time. And the only place where they coincide is here at 1 second. And I bolded everything here, so I'm going to super bold this by highlighting it as well. And then maybe move it up a skosh so it all fits on the slide. Right, so what we see in the pattern, if we look at these sine waves individually, this is the 3 hertz wave just repeating itself 3 times in 1 second. It's the 5 hertz wave, and again it just starts at 0 again whenever its period elapses, so at 1/5, 2/5, 3/5, so on and so forth. And they only kind of line up, these red lines where the period begins again, only lines up at 1 second, right? So that's what we're going to see for the complex wave. It looks like this, and this is kind of what I showed you in Prot there just a second ago. The period of this is 1 second. That means the frequency is going to be 1 hertz, just like what we saw here in Prot, right? This is expanded though over 3 seconds, so you can see how the pattern repeats. This is one complex pattern, and it repeats 3 times. Okay? It's happening because those individual sine waves line up and repeat again at the same time. Okay, so an important kind of consequence of this, and this I will also put on my Microsoft Word chalkboard. Each component wave will complete a whole number of periods within each period of the complex wave, right? So we'll go back to this, but this is kind of the main point I want to get across for now. They're only going to start repeating, or the complex pattern is only going to start repeating when both of the individual sine waves start repeating at the same point in time. So they're only going to line up when they're kind of back at 0. So that means they have to complete a whole number of repetitions within the same time frame if you assume they start from 0, right? So this one completes 1, 2, 3. This one completes 1, 2, 3, 4, 5, and then they line up again, right? You're not going to get this one completing like 1, 2, 3, 4, 5, 5.5, and then line up, right? Because it's starting at 0. If it completes like a half, then it's going to go down in 0, or it's going to be here, and we're going to get a different pattern because of that. They have to line up. They have to complete a whole number of periods within each period of the complex wave. We'll highlight that. Okay, so keep that in mind. And I'll go back to my tidbit slide. Okay, so if we combine a 6 hertz wave with an 8 hertz wave, let's think about this one as well. What should the frequency of the resulting complex wave be? And hopefully you can see at least the path to answer this question from what we've talked about already with respect to like greatest common denominators or maybe smallest common multiples, but I want to talk about it with respect to the multiples. And then another way you can think about this is, what would the period of the complex wave be that we form by combining these two sine waves together? These two questions have an answer that is, or answers that are related to one another, right? Frequency and period. So I'm going to let you think about this for a second. We're combining a 6 hertz wave and an 8 hertz wave. What's its fundamental frequency going to be? And then I also kind of, normally in class, the way I walk students through this is this way, by looking at what happens to sort of the repetitions of the patterns formed by these individual sine waves. So hopefully you can see, which I didn't walk you through with this previous slide, but the greatest common denominator of 6 and 8 is 2, right? So you can divide 6 by 2 and get 3. That's a whole number. You can divide 8 by 2 and get 4. That's a whole number. There's no number bigger than that that will give you the same result. So the answer we're expecting for frequency should be 2 hertz. And this is a little bit messed up. To ask another way, what would the period of the complex wave be? We can kind of figure that out in a couple of different ways. But if we know that the frequency is 2 hertz, then the period 2 hertz, then period equals 1 over 2. And we're going to measure that in a second. So period is just 1 over frequency. Frequency is just 1 over period. So our period should be 1/2 of a second, or 0.5 seconds if you want to put it that way. And we can see why here, right? So for the 6 hertz wave, it makes 1 repetition in 1/6 of a second. Actually, maybe I can't do it that way, not easily. And then also 2/6 of a second, and then 3/6 of a second. It's hard to say sixths. Anyways, this is 1/6 of a second. I'll write it out here for you. And this is 2/6, and this is 3/6. And 3/6 conveniently is 1/2 of a second. So for the 8 hertz wave, it's going to complete one pattern in 1/8 of a second. Might be a little more constrained here. Don't do that. Yeah, something like that. I think you can still see it. This is going to be 2/8 of a second, or 1/4 of a second. This is 3/8 of a second. And this is 4/8 of a second. And this is where they start to line up again, right? At 1/2. So we can complete one complex pattern in 1/2 of a second. That means we're going to complete 2 complex patterns in 1 second. That means our frequency is 2 hertz. But if we complete one complex pattern in 1/2 of a second, our period is 1/2 of a second, right? Okay. Hopefully that makes sense, but here's the output that you get if you generate this in prot using the formula way. This is a whole 1 second, and I see this complex pattern twice in it. That means my period is 1/2 of a second. The frequency is 2 hertz. I'm not going to say that again. Hopefully you get the idea, though. What I want to move on to is this guy, Joseph Fourier, who had a lot to say about this matter. So Joseph Fourier was a French mathematician. He was kind of working in the era of the Enlightenment, back when guys could be like know-it-alls and dabble in a lot of different fields and have important things to say about all of them. So he studied, among other things, heat and periodic motion. The periodic motion kind of links up to what we're going to talk about next, but the heat part is kind of funny or tragic, however you look at it, because Joseph Fourier came up with one of these kind of insane genius ideas that he would be healthier in life if he walked around everywhere wrapped up in blankets. Who knows why? And he did that for a while until one day he was walking around wrapped up in blankets and he wanted to go down the stairs, and then he tripped on the blankets going down the stairs and then like crashed to his death at the bottom of the stairs. And nobody ever heard from Joseph Fourier again. But it's okay in some respects because he got his Fourier's theorem published before that happened, and he will live on forever in that respect because this is a super powerful idea. And that idea is that any complex periodic wave can be constructed out of a combination of different sine waves. So no matter what kind of sound wave you get at all, you can throw them all out there as long as they're changing over time. You can boil that down to a combination of different sine waves. You can kind of figure out what the atoms of that sound are, and those atoms are sine waves, basically, of different periods or of different frequencies and amplitudes. That's an amazingly powerful tool to have at your disposal. We not only use it in things like acoustic phonetics, but we also use it to figure out, say, what the chemical consistency is of stars that we see like millions of light years away, or another tool that people use to figure out like where oil is in the ground, so on and so forth. There's a lot of different applications of this theorem because it is so widely applicable or just generally universally true. And with that in mind, I want to say for our purposes in acoustic phonetics, this also applies across the board, but in acoustic phonetics, when we're talking about these sine waves that go together to create complex waves, we're going to call those sine wave components of a complex periodic wave harmonics, which again is the main topic of this lecture. So you may have encountered the term harmonics in different settings. It's used like in music as well. It is related, but we're going to focus on it in that meaning in music is related to the meaning we get in acoustic phonetics, but we're going to focus on this really specific technical interpretation of this term, and I'll show you exactly how it works. So here's the cool thing about Fourier's theorem, and this is part that's also kind of applicable to astronomy and or maybe music, if you like Pink Floyd. Who doesn't like Pink Floyd? Anyways, Fourier's theorem implies that sound can be split up into its component frequencies, just like a prism splits light up into its component frequencies. So hopefully you know this, but if you don't, if you have white light and you put it through one of these sort of glass pyramids called a prism, that prism will split up that white light and give you a rainbow on the other side. And the different colors of the rainbow basically correspond to different frequencies of the photons in the beam of white light. We're going to do something similar here in acoustic phonetics, where we're going to take a complex sound on this side and we're going to split it up into its various harmonics on this side to see what it's made out of. Okay, to do that, we're going to create what are called spectra, or an individual one is called a spectrum or power spectrum. So what does that show us? Heretofore, we have looked at complex waves as waveforms, where on the y-axis we get amplitude or air pressure, and then on the x-axis we get time, how that air pressure changes over time. So another way we want to represent complex waves now is with a power spectrum, or just a spectrum for short. And for this, we're not going to be concerned with time. We're just going to provide a representation that doesn't involve time, so it doesn't change over time, and it's assuming kind of that the complex wave doesn't change over time either. But instead, it's going to show us what sine waves go into making that complex wave. So if you remember, each sine wave has two parameters that we care about. It has its peak amplitude and it has its frequency. Knowing those two things, we can describe any particular sine wave out there that we care about. Our power spectra will show us intensity, which is based on amplitude, and it's going to show us that on the y-axis of the spectrum. And then it's going to show us frequency on the x-axis. So frequency of the sine waves that are composing this complex wave. So that might be a little hard to just think about if I tell it to you, but so I'm going to show you an example of how this works. We'll go back to our very basic example of a complex wave where we had this waveform with high amplitude and low frequency. And if we plot that individual sine wave on a power spectrum, I'll walk you through the complex wave again. I thought I was going to go over to the right, but I'm going to go down first. But we'll add this one to this one. So low amplitude, high frequency, we get this complex pattern. That first sine wave will just look like this on a power spectrum. It's just going to be a spike. And this is a bit of an oversimplification. So it's plotting peak amplitude here on the y-axis. It gets a little more complicated when we see an actual power spectrum, and it's going to plot decibels. But this shows you how high in amplitude that particular sine wave goes. And then this is its frequency. So it should basically be a 4 here if it's 4 hertz. The next sine wave will look like this on its own power spectrum. It'll just be one spike because it's just one sine wave. And it only goes up halfway on the amplitude scale, and then it's higher on the frequency scale, more to the right, or I guess the way you're looking at it, I guess this way. Anyways, this is 12 hertz, but if we add them together, in this case, we can kind of see both waves in the finished product, and it's convenient, but not common that that's the case here. In a power spectrum, it's simple to see what sine waves make up the complex wave. So I get this guy down here, and I get this guy, and I add them together. They just both appear in the same power spectrum. They're just two spikes now rather than one. Anytime you have a power spectrum with more than one spike, you're getting a complex wave of some sort, right? These are pure tones or sine waves because they have one spike. Complex wave has more than one spike. And hopefully it's obvious you can add as many spikes as you'd like, basically, at different amplitudes and frequencies if you'd really like to. We're keeping it simple for now because it's complicated enough. Anyways, once you add those two sine waves together into a complex wave, all of a sudden they become harmonics. And they're not just sine waves by themselves, they're just component sine waves of a complex wave called harmonics. Okay, I'm going to go back to Prot and play around with kind of a similar complex wave as the one we created a while ago. I'm going to make this one 300 hertz and 500 hertz. Those are going to be the frequencies of my two component waves. You'll be able to hear them, which is nice. I guess I'll leave it at 3 hertz or 3 seconds. Yeah, they have the same peak amplitude. They just differ in frequency. I'm going to add them together. I'm going to get a complex wave. Okay, here we go. I'll look at it in a waveform view. Hold on a second, I'll turn this off. And it should look basically exactly like what we saw for the combination of 3 hertz and 5 hertz, except it's repeating a lot faster in time. So this is repeating about 0.01 seconds is about one period because it's 1/100th of a second. And I can kind of hear it. I'll play the whole thing here in a second. So if my frequency is going to be 100 hertz, that's the greatest common denominator of 300 and 500, then my period will be 1/100th of a second or 0.01 seconds. Anyways, we can compare it to this guy. Zoom out. And that pattern looks similar, right? And this is what it sounds like. Hopefully that's not too loud. Maybe knock it down a notch. And I think you can kind of hear the two tones in there. One's at 300 hertz and one's at 500 hertz. You can also look at the spectrum of this guy by going to this feature of Prot, which says Analyze Spectrum. Go to Spectrum. Normally when this is, when you first use this in Prot, this Spectrum Fast option will be clicked. Don't use that fast option. It's going to give you kind of a sloppy mess. Unclick that and then hit OK. It's really simple to do this. And then hit View and Edit. And lo and behold, we have two spikes because we added two sine waves together. They're just low on the frequency scale. But if I zoom in here and try to click on these guys, this should tell you what frequency they're at. So the frequency is plotted on the x dimension. So this first one's about 300 hertz. It's hard to click on exactly. The second one should be at 500 hertz. Right there. Did pretty well with that one. And I can play this in the spectrum. And it sounds like what I just played you. But I could also, if I want to, just zoom in on one part of this and play that particular sine wave. Yeah, and it's not changing over time, which is why I can just use the spectrum to analyze this, because I don't have to worry about time in this representation. So I've got frequency here on the x-axis, and then I've got intensity on the y-axis. This one goes up to about 90 decibels. That doesn't mean a whole lot. If I change the, it's not going to mean a whole lot to us right now, but if I change the peak amplitude, let's say I make this one 1/10 in terms of its peak amplitude, so 1/5 of the other one, we should see a bit of a difference there in the spectrum, in the height of the harmonics. So yeah, going back to here, the sound will sound different as well, but my higher frequency harmonic doesn't go up as high in the intensity scale. It goes up to 76 about. And this one's still at 90. And it sounds like maybe a little quieter. And this one, not as intense as this guy. Yeah. Anyways, that's how you get a power spectrum in Prot. What does that mean for us in terms of acoustic phonetics? So the fun part of Fourier's theorem, well, it's super powerful to begin with, and because we can kind of boil every complex wave down into sine waves. But the other part of it is that the component harmonics or sine waves of any complex periodic wave will all have a frequency that is an integer multiple of the fundamental frequency of the complex wave. This is like a super important and useful point, so I'm going to read it again. But Fourier's theorem implies that or actually proves that the component sine waves or harmonics of any complex periodic wave will all have a frequency that is an integer multiple of the fundamental frequency of the complex wave. I'm going to write that down, but it turns out you actually knew this because this is equivalent to saying that all component waves of a complex wave will complete an integer number of periods, a whole number of periods within each period of the complex wave. So I'll write this part down here and then kind of show you operationally what that means. But yeah, the component sine waves of complex wave all have a frequency that is an integer multiple of the fundamental frequency of the complex wave. Same thing as saying that each component wave completes a whole number of periods within each period of the complex wave. Yay! What does that mean? So let's say I have a complex wave with a fundamental frequency of 100 hertz, like the one I just produced. Then it's only going to be able to have harmonics at these frequencies. The first harmonic or the lowest harmonic frequency could be 100 hertz. The second could be at 200 hertz. The third could be at 300 hertz, 400 hertz, 500 hertz, so on and so forth, all the way down the line. You're never going to get a harmonic in this complex wave with like a frequency of 150 or 167 or 231 or whatever. You're only going to find harmonics at these specific frequencies that are all multiples of 100 hertz. So in the example I gave you, we added together two sine waves. One had a frequency of 300 hertz, and the other had a frequency of 500 hertz. So that works. What we're not seeing any harmonics at these lower frequencies like 100 or 200 or 400. This is not guaranteeing that you will have some harmonic at these frequencies, but if you do have a harmonic, it's going to be at one of these frequencies, basically. And when you add together two sine waves of 300 and 500 hertz, that still fits. They wind up with a fundamental frequency of 100 hertz. They just don't have other components at these frequencies, at these other frequencies. So let's think about this, and normally ask this in class as well. And this is basically a bit of math or arithmetic, really. But let's say we have a complex wave of a fundamental frequency of 440 hertz. What are the possible harmonic frequencies for that guy? Where would I find sine wave components in terms of the frequency scale on my power spectrum? Remember, this is could, but not necessarily will find harmonics at these frequencies. And for this, you just have to do a simple bit of math. So the first harmonic would be at 440 hertz. I'm picking this frequency, by the way, because it's the concert A, going back to music. It's sort of the A above middle C on a piano that everybody tunes to in an orchestra, if you've ever had the pleasure of doing that. The first harmonic would be 440 hertz. The second would be 2 times that, 880 hertz. And eventually, at some point, you'll probably have to break out a calculator to keep going. But like 3 times 440 is 1320. 4 times 440 is 1760, so on and so forth, all the way up the scale. And it can go up to like infinity, basically. But it can't be anywhere in between these numbers. There will be no harmonics in between 440 and 880 if you have a complex wave with a fundamental frequency of 440 hertz. Okay, that's cool. That gives us a lot of structure to work with when we're dealing with what seem like impossibly complex objects, like these sound waves that we're analyzing. But for complex waves, the frequencies of the harmonics are always going to depend on the fundamental frequency of the wave. Actually, this is a really nice, useful, important point as well, so I'll write that down on my fake blackboard. For a complex wave, the frequencies of the harmonics are always going to depend on the fundamental frequency of the wave. So just thinking about it a little bit backwards, up until now, we've been adding sine waves together to get a complex wave and then figuring out what its fundamental frequency is. But in speech, things work in the opposite direction of that. So yeah, actually, let me show you this little demo first. We'll go to this 440 hertz sawtooth wave. So I have what is called a sawtooth wave here, which is not a sine wave. It is a sound wave, but it's called a sawtooth wave because it has this pattern, which looks like the teeth of a saw, and it's pointy on the bottom and the top, and it's repeating over time. So this is a complex periodic wave. Here's a little snippet of it, like that. This particular one has a frequency of 440 hertz. Doing really well talking today for phonetics class, but we'll get there. This sounds like this. It's an annoying sound. It kind of cuts through your eardrums like a saw, maybe. Maybe not that bad. But that is what it looks like in waveform form. Actually created a spectrum here. I'll create it again. If I look at the spectrum of this guy, I will see frequencies of sine wave components exactly where I thought they would be. So my first harmonic is at 440 hertz. Get closer. I can get more accurate. 440. Second one should be at 880. Third should be at 1320. Fourth should be at 1760. Fifth at 2200. We haven't done the sixth, but it should be at what, 2640? Thereabouts. Yeah, my harmonics are exactly where I expect them to be because they're all multiples of the fundamental frequency, which is 440 hertz. And again, I can kind of just play parts of this on the spectrum view. Those are the lower frequency harmonics. These are the higher ones. This might be a little annoying. Yeah, not too bad. Anyway, or just grab one, that individual harmonic. Yeah, they're all an A in concert music. But for our purposes, what matters is that they're evenly spaced apart from each other. They form this really nice pattern. They're evenly spaced on the frequency scale, and then they kind of consistently decrease on the amplitude or intensity scale. That's how you get that sawtooth pattern. I've got one at 150 hertz here as well. It's going to sound lower in frequency, like a low buzz. And it looks the same in terms of its waveform, like that. And we can look at its spectrum as well. Where would we expect to get harmonic frequencies for this guy? Well, again, similar pattern, evenly spaced harmonics, decreasing in kind of that nice parabolic shape. My lowest harmonic should be at 150, second at 300, third at 450, so on and so forth. Just multiply 150 by 1, 2, 3, 4, all the way up the scale. Yeah, something like that. Okay, cool. I was going to tell you a little bit about how speech works. I'm going to wait for that here in a second. I'm going to tell you about another representation before we get to that. So spectrograms are a three-dimensional view of sound, which turns out incorporate the information we get in a spectrum or a power spectrum, and also add time to it. So those wind up being super useful. So we get the same dimensions that are found in power spectra. A spectrogram is going to plot intensity on the z-axis or z-axis, if you want to do that sort of thing. And then it'll also plot frequency, this time on the y-axis. And then it's going to add time on the x-axis. So hopefully I can get this. Maybe I'll do it like this. So we've seen power spectra that kind of look like this, right? This is the lowest frequency. Hopefully I've got the right orientation, like the video camera. And then the harmonics, the intensity of harmonics kind of decreases as they go up the scale. So what's going to happen when I look at this in a spectrogram view is that I'm going to turn the power spectrum on its side so that it kind of points at you like this. And the more intense harmonics are going to be darker shaded in the power spectrum view. And actually, wait, hold on a second. So if you're looking at it this way, then this is the higher, I can't even do this. it's going to look like this. All right, so this is lower frequency, this is higher frequency, less intensity. You're going to see it like this in the spectrogram view. So this is the lowest frequency but most intense. It will appear to be darker shaded, and then as we get up to the higher frequencies, it'll be less shaded. But basically the idea is you kind of have to do a translation of frequency, so it's on the y-axis, and then intensity is on the z, or pointing through the representation. And then time is on the x-axis. So that's also kind of a funny thing. So let's say I have, we'll do it this way. Let's say I have like one power spectrum like this at one point in time, and then later on it'll change to like this power spectrum, like that. So I wind up like having this representation at this point in time, and then later on, I'm trying to think of how you guys are seeing this. It's going to look like this. Yeah, it's going to look like this. So the intensity might change over time, right? Starts like this, ends like this, and it goes like that in a spectrogram. So I just keep adding spectra like that over time as I go. And so we can see that way how the spectral features change over time as well. Okay, so back to Prot, and I want to make up a more complex sound than what we've heard before. I've got my little formula there at the bottom. I may be having too much fun with this, and this lecture may be going over time, but it's my last one, so you're going to have to roll with it. Okay, so this one has the same 300 hertz component there. Then I'm going to add one at 2100 hertz, and then one at 3300 hertz. So this second one has a peak amplitude of a 10th, and the last one will have a peak amplitude of a 20th, or 0.05. This one is 0.1, and this one's at 3300. Label it appropriately, and what do we get? I'm going to tweak this a little bit so you can see the spectrogram a bit better. But the spectrogram is down here on the bottom part of this representation, and we can see our 3 component sine wave frequencies. So one at about 300, 2100, and 3300. And they're not changing over time because we haven't done that yet. We can look at the complex pattern if you really want to. It's pretty complex. Like that, isn't that cool? Looks like maybe some beetle or symbol or something. I don't know what. Anyways, what does it sound like? Yeah, I'm gonna make this shorter so we don't have to listen to it for 3 seconds every time. But let's listen to it again, maybe a little bit louder. So if you were to pick, say, one vowel that we know to sort of identify the sound as, or maybe what vowel does this sound like? Pick one, let me know what it is. And here's a short version. Most people in class will say E for that particular vowel. Maybe you did too. But all I've done is add sine waves together at these 3 frequencies. And all of a sudden I'm getting something that sounds like an E. And we can look at it in a spectrum view as well. And it should look like what I promised, with component frequencies at these, component harmonics at these 3 frequencies. Yep. Anyways, that's just one unchanging sound. What happens if sound starts to change a little bit? Let's listen to some of these sound samples, and you can tell me what you think is going on here.
Where were you a year ago?
I'm going to play that a little bit louder.
Where were you a year ago?
Yeah. Does that sound like speech to you?
Where were you a year ago?
Because it's not. This is speech.
Where were you a year ago?
This is just somebody taking 3 sine waves, putting them together, and having them change frequency over time.
Where were you a year ago?
And you can kind of understand what that is trying to say. It's this, right?
Where were you a year ago?
Let's try another 2. Here's this one.
Kick the ball straight and follow through.
This first one works really well. This one is a little trickier. It kind of got cut off there too.
Kick the ball straight and follow through.
It's supposed to be...
Kick the ball straight and follow through.
And there's the last one here.
A steady drip is worse than a drenching rip.
Yeah, somehow that got cut off as well. I'll play it again. Maybe you can guess at what it's saying. Yeah, so these are a little weird, but this one is supposed to say,
The steady drip is worse than a drenching rain.
and if we listen to it again, maybe you can understand it better. It gets cut off there a little bit at the tail end. But these are called, this is called sine wave speech, because like I said, this was put together, they just took 3 different sine waves and had them change in frequency over time. And you get something that sounds like speech from that. They're based on some of the features of speech. We'll see what those are next time. But basically, one of the fundamental characteristic features of speech sounds is that they exhibit spectral change over time. They don't really sound like this. This is kind of close to speech, but since it's not changing, it just sounds kind of also like a computer sound. This sounds like computer sounds, but also you can get the perceptive speech out of it too, right? That one's usually pretty easy to get for beginners especially. Yeah, so hopefully you got that effect. So here's what I wanted to say about how speech works. So remember, when we are producing voiced sounds, we have trilling going on at our vocal folds. And that's going to create a complex wave with a fundamental frequency. We talked about that when we looked at like tones and whatnot, and how frequency changes for stressed versus unstressed syllables. F0 goes up and down in speech, right? But it basically, F0 comes from how often our vocal folds open and close when we're voicing some sound in speech. That's going to create, that complex pattern of the vocal folds opening and closing is going to create a series of harmonics, which will enter into the vocal tract through your vocal folds. So all of a sudden you're getting not just one complex wave, but you're getting complex wave which consists of a whole bunch of sine waves at different frequencies. The frequencies of those harmonics, those sine waves, are going to be evenly spaced apart from each other. So that spacing is going to entirely depend on the rate at which the vocal folds are vibrating, right? So if my vocal folds are vibrating at a fundamental frequency of 100 hertz, I'm going to get harmonics at 100 hertz, 200 hertz, 300 hertz, 400 hertz, so on and so forth, right? We can't change those frequencies of the harmonics independently of one another. They have to be evenly spaced according to whatever the fundamental frequency is. So the question is, we know that once sounds start exhibiting spectral change, they start to sound like speech. And this is in fact the fundamental characteristic of speech sounds altogether. But how do we get those spectral changes that we need for speech if we can't change the frequencies of the harmonics independently of one another? Think about that for a second. And maybe you can think of the answer because it's the other half of the sine wave equation, basically. It's the intensity of the harmonics that we can change. So remember, every sine wave has a frequency and an amplitude. The amplitude kind of translates into intensity at some level. If you can't change the intensities if you can't change the frequencies of the harmonics independently of each other, you can change their intensity. And that you can do using the acoustic phenomenon of resonance. And I'll give you one example of how that works with this sound file here, which is, I'll just let you listen to it. All right, that was kind of unusual. But this is a type of singing, sometimes called throat singing, but maybe more appropriately would be called overtone singing, or maybe harmonic singing. It's another way to say it, but Anyways, this is what the spectrogram looks like for this particular sound file. And I'm going to play it again and just kind of walk you through the basics of what we see here in the spectrogram. So this is a complex wave, and it has harmonics at evenly spaced intervals on the frequency scale. You can see them going all the way up here, the frequency scale. And then what the singer does, what he has figured out how to do somehow, is to focus on individual harmonics and make them more or less intense. So he goes up this scale of harmonics and makes each one more intense, and it becomes darker in the spectrogram view, and the others around it become weaker or fade out, basically. So you can kind of hear him walking up that scale of harmonics. And then as he does so, I'll play it one last time before we're done. As he does so, maybe you can think about like what vowels does it sound like when he's producing kind of the various parts of this sequence. Just think about that, and we'll walk through it one last time. All right, I'm going to stop there. Hopefully you came up with an answer for those vowels, but I won't tell you what I think it is. What I think mine is. We'll talk about that again next time. We'll also talk about how you can actually get this to work. How do we use resonance to change the intensity of harmonics in speech or music or whatever comes out of our mouth? So I'll see you then.